It's a joint work between Li-Jing Jiao, Li-Cheng Wang, and Yilu Sun. Li-Jing will lead the talk.
Okay, thank you. Good afternoon. My name is Li-Jing Jiao. I come from Beijing University of Post and Telecommunications. This paper, our most important contribution is the construction efficiency. In previous constructions, their running time may be several days or several weeks. Well, in our constructions, our running time just is several minutes or several seconds, and you get the same result or better result. Okay. This presentation includes three parts. First is background and motivations. Second is efficiently construct lightweight MDS matrices. Third is efficiently construct involuntary Hadamard MDS matrices. First, because previous presentations have introduced the background, so we directly go to our motivations. Okay. The first motivation is also the efficiency. In previous constructions, they usually use the following structures. They are circulant matrix, Hadamard matrix, optimal matrix, special, or other matrices. In these matrices, entries are repeatedly used or computed by others. Their main purpose of this is to reduce the search space. And we know that if the entries are independent to each other, then the search space will be very huge, and the running time will be unacceptable. Well, in this paper, we attempt to construct with the following new structures, S1 to S5. And the non-identity entries are independent to each other and are not repeatedly used. So we must find an efficient method or some law to construct them. Otherwise, we cannot finish our construction in an acceptable time. This is our first motivation. Second is entry. In previous papers, there are two main routes to select entries. First is matrix representation of finite field. Second is the site of all non-singular binary matrices, GL. The two routes have their advantages and disadvantages respectively. For instance, over finite field, the construction will be very efficient, but when the M is 8, over finite field, there is no element with one XOR count. Because we want to construct the lightest result, so elements with one XOR count should be used, but finite field doesn't have. So finite field is not suitable to construct the lightest result. Second, GL. Over GL, latest result can be obtained, but the search space is very huge, so the time will be very long, maybe several days or several weeks. And if the entries are independent to each other, time may be several years. So in this paper, we attempted to find some site to select the entries. And with this site, constructions will be efficient, and the result have as few XOR count as possible. Second, efficiently construct the lightweight MDS matrices. Next, I will introduce our main ideas. First is structure matrices. In our final constructions, we use the 5 structures. Someone will maybe ask, how do we choose them? The main method to select the structures is that there is no submatrix like the red one. Due to requirement of MDS, all submatrices should be of 4 rank, but the red one is not of 4 rank, so it should not be included. And moreover, the file structures is not equivalent to each other. For instance, S1 cannot be transformed to become others by exchanging some rows and some columns. Others are similar, so these 5 are not equivalent to each other. In this page, we introduce how we select entries. We select entries from the matrix polynomial residual ring. We do as follows. Let T be a non-singular binary matrix. Fx is the minimal polynomial of T. It satisfies Ft is 0. And we know F2T is isomorphic to the polynomial residual ring generated by Fx. F2T is the matrix polynomial residual ring generated by T. And in our constructions, we process candidate with the following one. In these matrices, some entries are T, and others are polynomials of T. And T's XOR count is 1. In this way, entries with 1 XOR count are directly used in the constructions. In this page, we introduce how we identify 4 rank. And with the 4 rank, we can identify 4 rank, and with the 4 rank, we can identify MDS. For instance, the left one is a submatrix, and in our algorithm, we process the middle one. And when we want to identify 4 rank, we just compute the determinant and get a polynomial. Next, we substitute T into the polynomial and get the fourth power of T plus I. Finally, we know that the submatrix is of 4 rank if and only if fourth power of T plus I is non-singular. This is our main method to identify 4 rank and MDS. Because in this paper, T is very important, so T should satisfy some conditions like follows. T's XOR count is 1. T is non-singular, and T plus I is non-singular. Why is T plus I non-singular? Because that. In these structures, if there are at least 2 T in one of them, then there must exist a submatrix as the following matrix. Due to requirement of MDS, all submatrices should be of 4 rank. So we have that the submatrix is of 4 rank if and only if T plus I should be non-singular. Before constructions, we analyze polynomials of T. For instance, T's order is 8, and T satisfies those 3 conditions. By searching T, we get the number of T is about 28,000. And the minimal polynomial of T only has 7 choices. In any F2T, there are at most 4 elements with no more than 3 XORs. Because we want to construct the latest result, so elements with few XORs should be searched and should be searched. Yes. In this page, we introduce our algorithm 1. Step 1: select T satisfying those 3 conditions and find its minimal polynomial, its Fx. Then find B1, B2, B3, B4 satisfying BT's XOR count is no more than 3. Next, step 2. Construct a candidate over the side of B1, B2, B3, B4. We can get like the red one. Next, we will identify whether it is MDS. So, step 3. If the matrix is MDS, then output the right matrix and its XORs. This is our algorithm 1. Next, I introduce comparisons with previous papers. In this page, we compare with LB16. And entries are matrices of order 4. Their running time is about 1 week, while ours is less than 2 minutes. Our number is a little small, but our time is very short. Here are our platform. This page we compare with LW16. Entries are matrices of order 8. For circulant matrix, our results are same. Their running time is about 3 days. Ours is about 1 minute and 27 seconds. For Hadamard matrix, their running time is about 4 weeks. Ours is about 7 minutes. And our number is much more. Here are our platform. This table is about all our constructions with algorithm 1. First part, entries order is 4. Second part, entries order is 8. Third part, entries order is 16. The last column is the running time. Only the S1, the running time is a little long. Others is several minutes or several seconds. Third, efficiently construct evaluatory Hadamard MDS matrices. L is an evaluatory matrix if and only if second power of L is equal to identity matrix as the following equation. The right one is a big identity matrix. The symbol denotes the following Hadamard matrix, and we prove a theorem about Hadamard, evaluatory Hadamard matrix. It is T belongs GL. Fx is the minimal polynomial of T. ABC are polynomials. Then the Hadamard matrix is evaluatory if and only if the following equation holds. According to the theorem, we make a little change and we get a special case. We just change the AX into the X. Others are same. Why we do this? Because we want to construct a lighter result than previous papers. So entries with 1 XOR count should be used. And in this paper, the entry with 1 XOR count is the T matrix. So in our constructions, as X is the T, BX, CX are BT and CT. So this is our main method. According to the special case, we do as follows. GOX satisfies the equation. Let CX is equal to BX plus GOX. It is equivalent to BX plus CX is equal to GOX over F2. Therefore, the following equation must hold. And then the following equation is same as the former equation. And we can see that we just change the Cx into the Bx plus Gox. And the Bx plus Gox satisfies the condition. So the last Hartmann matrix must be involutory. In this way, we can efficiently construct an involutory Hartmann matrix. Similarly, before constructions, we also analyze polynomials of T. For any T of order 8, satisfying those three conditions, they are T's XOR count is 1, T is non-singular, T plus I is non-singular. Then its minimal polynomial only has 7 choices, as mentioned previously. Here they are F1 to F7. For each Fkx, we compute all Gx satisfying the following equation. The equation, like the last page, is the equation 1. This page, I will introduce the algorithm 2. For instance, with the F1x, the equation 1 has 16 solutions. They are G1 to G16. So algorithm 2 can be shown as follows. Step 1, search Bx over polynomial residual ring generated by F1. Step 2, K from 1 to 16. Directly construct an involutory Hartmann matrix as the following one. Step 3, if the matrix is MDS, then output the result and its XORs. This is our algorithm 2. Next, we compare with previous papers. And in this page, we compare with LW16 again. Entries are matrix of order 8. Our result is have much less XOR count. And their running time is about 1 day. Ours is about 1 minute. And I should point that in our structure, only A is changeable. Well, in our structure, A, B, C are all changeable. Here are our platform. This table is about comparisons with previous papers. First part, entries order is 4. Second part, entries order is 8. And our result is much later than previous papers. That's all. Thank you for your attention.
Thank you. We have time for a short question. Anyone? I have a short one. When you introduce these 5 matrices, which are not equivalent to one another, are there only 5, or did you choose 5 out of all the possible ones?
Because I want to construct the lightest or construct the result with as few XOR count as possible. So yes. Identity should be included as many as possible. And the 5 structures should be not equivalent to each other.
Okay.
This is my idea.
Yeah, so it's all of them. There are no other such matrices.
Others. I think others may be okay, but I choose them.
Okay. Thanks. Last chance. Okay. So then let's thank the speaker again.